Hello everyone, I'm Nikhil and today we are discussing about deep kNN for medical image classification. So my topic is deep kNN for medical image classification. I took this topic because actually I'm doing my BTech project and in that project we are, my main goal is to detect breast cancer and while in that project we are been provided with very less data and doesn't have any labels. So I thought like this paper will be helpful for me if I present it and it will be I will make it better use of this. So the table of contents are like introduction. In introduction, we'll be having why deep kNN, why will be using it, and there'll be many methods for small classes. Why you only deep kNN will be using, and in second, secondly, we'll be discussing about deep kNN, like formation and neighborhood setting in kNN and comparison with the original model, original triplet function. And third thing, we'll be discussing about experiment. The results of the experiments and the compatibility of this algorithm. And finally, the end. So when it comes to introduction, so basically, the amount of data available for training a model is often limited to diseases in medical imaging tasks. So you'll see in some medical imaging tasks, you'll be having very less data to actually train the model and to test this because like the images, if you see some techniques, there'll be only a few images available and only few available data. There'll be only few data available data sets, so it will be difficult to create a model and train it. And however, they'll be having some techniques like fine-tuning model, meta learning techniques, kNN and metric learning. So basically, fine-tuning is like adding an extra layer to the pre-trained model and tuning them such that according to the input data, so that the model will be generating the exact outputs. However, like this model will be having its own limitations. Like if the image, see the pre-trained, the pre-trained data image data set is completely different from the data set that is we have, then the results will not be completely accurate. So for this kind of thing, they'll be having some meta learning techniques. Meta learning in the sense like they'll be having a metadata of the image and the training have to be done by taking them into consideration. But when it comes to small classes, like it can be useful in practical thing. And the another approach is like kNN. kNN is neighbor classification. So where features and dimensional reduction are often performed to obtain concise vector to represent the original determinant independent of the classification task. But it is having its own limitations, like features may not be discriminative enough. Like we can't discriminate the exact features when it compared to normal CNN and everything. And another form is metric learning. Metric learning can be applied to exact features into the unit feature space when they are transformed. Like features become more discriminative as neighbor methods. It depends upon the originality of the task. So like how it is, exactly, to learn to learn the extra discriminative features directly from the image data. uh, we have developed, in this paper we have developed, actually there is a triplet function to extract the discriminative features. But like in this speech, in this paper, see, we are having these many techniques, but you can see for each technique we will be having each limitation. So we developed one uh, deep kNN task, deep kNN algorithm, and we developed one loss function. So that we'll be discussing. This. So this paper was an end-to-end learning strategy to unify the kNN classification and feature extraction process. So what we exactly do is, here we take the kNN model. We take the kNN enable and we unify it to the feature extraction process. I mean, like you can see any models like resonant, ImageNet, and everything. These are the things that we use for feature extraction process, and we both unify them to classify small classes. So, what is deep kNN here? Like as we discussed before, here we combine feature kNN, feature learning, and kNN search to unify process for kNN classifier. And problem formulation. Here we use novel triplet function to solve this challenge. Uh, Discussing about the formulation, here f of xi comma t, f of comma uh, k comma theta t minus 1, where theta represents the parameters of feature extractor to be learned. See, for t minus 1 ith t minus 1th training iteration, f of k comma t minus 1, where theta represents the parameters of the feature extraction to be learned. So it is the feature extractor f of theta minus 1 is the representation. Also, uh, xi represents the for ith training image, xi represents is k nearest neighbor of the same class. After t minus ith iteration, yi represents, I mean, like yi comma y something yk is the, it represents the m nearest neighbors from other classes, and after t minus iteration, zm represents the uh, sorry, I said it wrong. Shit. So xi represents the sorry, yk represents the, wait 1 second. So sorry. YK represents the k nearest neighbors of the same class, and ZM represents the m nearest neighbors of the different class. So this is the difference. I'm sorry. And XI represents the turning image. So here what we discuss is f of x comma t is the feature extractor. So with this thing, what we can say is from the first equation, f of xi comma theta t minus f of yk comma theta t plus alpha less than you see the right RHS. So it means the difference between the I mean to make any that means among several the nearest neighbors of any specific image, one or more neighbors may not be from the same class as training image. To make any image and its neighbors belong to same class, the feature extractor and its image neighbors belong to same class. The feature extractor needs to be updated such that the distance between the image and any of its nearest neighbors is closer than the distance between image and any of the other classes. So we need to make sure that this equation follows as the distance between the image and its nearest neighbor, same class nearest neighbor. Same class is the keyword here. Same class neighbor must be less than the difference between uh, image and its different classes. Nearest neighbors have different classes. This is the thing that we have to make sure. And by moving it to this side, we'll be having the loss function, and here it is, as we like, I mean, this is the loss is zero when equality constant is satisfied. See, d of d plus equal to max of 0 comma we can see, and becomes larger when the constant is further from the being satisfied. Considering all n images in the loss function can be described as and the following are the loss is in equation 3, and this is the formulation for this problem. And here we see neighbor sets during training. So for each training image, it's k neighbors of the same class and m neighbors of the other classes will be searched as we discussed before and updated before updating the feature extractor in the next iteration. So this, I mean, this is followed as a chain such that searching these two images, I mean, these two like kNN neighbors of the same class and elimination of the different class, the differencing them and then updating from the next iteration. This is the thing that we do. And during this training process, like the non-parametric kNN neighbors such players role of the predicting data at each iteration. So I mean here we see the non-parametric kNN tables, the parameters that is then involved in the uh, search role providing data at each iteration. Like I mean these provides data for each iteration, such is not involved in the derivative of extractor parameters. Uh, Therefore, with this we can see the difficulty in differentiating the non-parametric process naturally like I mean we are not easy, but I mean when it comes to novel triplet class, I mean that we discuss next about traditional triplet. So uh, here in comparison to traditional triplet class, here what I actually did is traditional triplets are formed often by the furthest within class pairs and nearest cross class. So here we take all the within class pairs, and before we did here we can see we are ignoring the non-parametric. I mean we are taking only few within class pairs and few without neighbors which are not in class. But in the novel I mean, with tradition within traditional triplet class, we take all the within class parameters and we take few cross class pairs. When see like this is the difference between two, and with this thing we can explain this part like. Uh, you see the non-parametric kNN neighbors. This part can be explained with the help of this. And the proposed method only requires any data and its kNN neighbors of the same class are closer than the distance between data and other class. I mean, this we can see with the help of this. The proposed approach can be used to train a deep kNN by combining the two steps of kNN classification. Okay, fine. The traditional triplet loss can be used to train deep kNN. I mean, you see, with the, as we discussed about the algorithm, in the case of traditional proposed triplet laws, we take only few of the near and few far by combining the two steps of client classification. The two steps of client classification is taking the extraction and classifying. While the traditional triplet law, it involves all the feature uh, within classes, which we cannot be done. And this is the just I mean brief discussion about deep kNN. And here we come for the experiment to carry, I mean, to determine what exactly happens here, we made an experiment setup. See, in this experiment setup, we carried out with two skin image datasets, one pneumonia X-ray dataset. So, in the case of skin dataset images and pneumonia X-ray images, the images were initially 256 cross 256, and these were cropped into 224 224, followed by random odds and ends that we know. And during training deep kNN, the batch size B varied a bit for different datasets due to varying the scales of datasets. So for skin 796 and pneumonia, the dataset size is 96, and for SD 198, the batch size is 90. To guarantee kNN neighbors of the same class for each image in a batch, particularly on SD dataset, the satisfied sampling was adopted. And during testing, all training test images were fed into trained feature extra only once to get corresponding feature vectors. That we can be seen here. And this is the brief about the experiment setup. And here we discuss about the effectiveness of the deep kNN compared to all the other models. So we have used here to demonstrate the effectiveness of the proposed kNN. Uh, we took several baseline methods such as two baseline class, I mean kNN class with that VGG 19 dozen 15, which VGG 19 is used for medical classification, and one and like which were I mean, we represently built on feature expert part of which 50 retrain and immediate. The other baseline can interpret. I mean the other Mm, I mean, like you see the third part here. The one second, this thing. Then other Bayesian kernel triplet was built on feature extractor training with. This was built on feature extractor trained with traditional triplet laws and using pre-trained Resident 50 on imaginary dataset. So, like imaginary data is used as a backbone here, and on the Resident 50, which was built on feature extractor with traditional triplet loss, and the same Resident 50 was trained with the proposed deep kNN strategy. And the fourth thing, the same Resident 50 have been trained, and this is the like here are the KP values. KP denotes the number of nearest neighbors used in testing. Uh, and we'll discuss about this next. So let's go to the next. So first thing, like mm, 1 second, yeah, can Resident 50, Resident 50 phones. The same Resident 50, I mean, like that we have discussed now. Here we see the accuracy at each of our deep kNN is compared more than all the remaining models. This can say that this deep kNN outperforms the remaining three compared to, I mean, when it even out model is triplet resonant function. So this can be examined from this like table that we have developed. And coming to this part, weighted, I mean, C, and like this thing. So we we also compare deep kNN with CNN classifier of same resolutivity backbone that we used before, and standard deviations for over multiple runs are within range of 0.5% to 1.2% for accuracy, mean class recall, and the recall on the small class in the experiment. The overall performance of deep kNN cross entropy, like this part that we have discussed here, that we are discussing now, is like, see, here the accuracy is more when it compares to weighted cross entropy resistance. And this is the part that, I mean, this table shows the effectiveness of the deep kNN and deep kNN with MLP. You see, MLP is multi-layer perceptron. So in some scenarios only feature vectors were originally available in dataset, but in the case deep kNN learning strategy, like in that case, I mean, the deep kernel, it also works because the feature vectors are originally available in the dataset, and apart from that, like to demonstrate the deep kNN under MLP backbone, what we take is like we'll be taking this methods like, like normal. We'll be all checking with kNN basic and uh, LMNN, MLP plus triplets is the see, I mean, uh, the triplet is the traditional triplet loss, and the cross entropy loss MLP plus CE. The neighborhood component analysis NCA that we are here. NCA is the neighborhood component analysis that we can be checked with the neighborhoods, and it is part of some similar to kNN but not kNN, and the large margin nearest neighbor. So that is, LMNN is a technique which can be used for this kind of purposes. And this is the thing that we have discussed before. And when we use MLP plus deep kNN, MLP means multiple perspectives. This can be added at the end of the feature extractor and fine-tuned accordingly. Then the accuracy I mean, is more compared to all the other remaining models. And the main class recall also is more compared to all the other kNN basics in CA and LMNN and MLP plus CA. This is a thing that we can be extracted with the help of in this thing, and speed of convergence. So when it comes to speed of convergence, it was observed that the proposed triplet loss takes much fewer epochs than the traditional loss to reach the same level of accuracy, fostering convergence, regardless of the model states in database. So it can be take very less. I mean, like when you take two models, if model A takes much epochs to converge to some point, then our deep kernel takes only few time to come to the same point to get converged. And this deep kNN learning strategy requires only that each sample and its kNN. I mean, like in this deep kNN, we require only mm, the same. I mean, same sample of the. I mean, we'll be taking only few samples where it comes up normal traditional triplet class. We'll be taking all these samples of the same class and few samples from different class. In normal, the triplet function that we propose, we take only few classes from the same and few. I mean, few neighbors from the same class and few neighbors from different class. Here we can see the computationally traditional triplet stars takes much time and much uh, yeah, like RAM and everything, where our triplet stars only depends upon the inner circle of this thing and flexibility of the architecture. I mean, we have tested deep kNN with 4 widely used kNN, and the accuracy, WebCR, and RS of the uh, with each and every model's architecture is here described. So deep kNN is different background perform slightly different, but all outperform the corresponding strong basic kNN. Demonstrating the deep kNN learning strategy is robust to structures of feature extractors. Additional evaluation shows that the deep kNN is also robust to hyperparameters k, where k, could be a same class, different class, and the number of class, I mean, same class test images. And this is all about deep kNN. And finally, we introduced a novel deep learning approach. It's called deep kNN, which is for first time unifies the feature extraction kNN. Before, we doesn't have any. We use kNN classifier to just classify, but we never integrated kNN with feature extracting. And I mean, we have seen this outperforms all the available kNN classifier, and therefore deep kNN provides a new approach to diagnosis of disease with limited training data. Thank you.